Hi, my name is Philip. Today I will talk to you about the CPT and the CPT plus algorithm for sequence predictions. Those are two algorithms we use to do prediction for a sequence. You have a sequence of something and you want to know what will happen next. So these are some useful algorithms. And at the same time, I will talk to you also about some other classical algorithms such as the PPM, AKOM, and so on. Okay, so let's start. I will first introduce the problem of sequence prediction. The problem of sequence prediction is not very complicated. You have some sequence of symbol, as you can see here, like A followed by B followed by C, and then you want to know what will happen next. Okay, so for example, you go to A, maybe is to go to the gym. B means to go to restaurant. C means to go to the movie theater. And then you want to predict where the person will go next. Another example is, for example, when you type on your cell phone, you type some words, hello, how are, and then you want to know what will be the next word, like how are you, for example, and so on. So you want to do the sequence prediction. So here, what we mean by sequence, it is a sequence of symbols, not numbers, like some words or some sequence of location, or it could be other kind of sequences. There are many, many fields. Okay, so the problem of sequence prediction is giving a set of training sequences. We want to predict the next symbol of a new sequence. So maybe we have a lot of sequences about where the people go in a city. They go to the gym, they go to the house, they go to school. And now we have a new sequence and we want to predict where the person will go next. Some other applications are, for example, to predict the next web page that you will visit. So if we know which web page you will visit next, we can load the page before to make it faster. To analyze the behavior of customers, if you buy A, B, then what you will buy next. Or product recommendation, and so on. Many, many other possibilities. Okay, so how to solve this problem? The general approach is as follows. You have some training sequences that we saw before. Okay, we know A followed by B, by C, and so on. And then we want to use these sequences to build a model that will allow us to do some prediction for new sequences. So we call this a sequence prediction model. So the first phase is training. We have some training sequences. We build a model, and now we have a model to do prediction. Now step 2 is to do the prediction. So we have a prediction model, and now we have a new sequence like ABC, and we want to know what will be the next symbol. So we use a prediction algorithm like I will show you today, and we get some prediction. So after ABC, the model think it will be D after. So maybe after school, restaurant, and gym, we think the person will go back to home, maybe. Okay, so there are many ways to solve this problem, to do the prediction. One way is to use what is called sequential pattern mining. So I will explain very briefly the idea. Maybe you know already about this, okay? So the idea is sequential pattern mining. You have a table with many training sequences on the left. So for example, sequence 2 means A followed by D followed by E. Sequence 3 means E followed by F followed by G, and so on. And we can use some algorithm like prefix span to find all the subsequences that appear many times in these sequences. So if we set a parameter we call the minimum frequency or support to 33%, we want to find all the subsequences that appear in at least 33% of our training sequences on the left. So let me give you some example to show you about this. Here we have one pattern is A followed by D followed by E. This A followed by D followed by E appear in 50% of the training sequences. So A followed by B, A followed by D followed by E, A followed by D followed by E, A followed by D followed by E. So it appears 1, 2, 3, S1, S2, S4 out of 6 sequences. So that means 50%. And since it is more than 33%, we say it is a sequential pattern. So in this approach, we have the training sequences. We apply the algorithm like prefix span or CM spade and so on, and we find some patterns. And then we can use these patterns to do the prediction. So for example, now if we have some person do A and D, we want to know what she will do next. We can look at the pattern, and we know that A, D followed by E appear 50% of the time. So we can recommend it will be E, or do the prediction that it will be E. So this is one approach. We use the pattern to do prediction, but one drawback is that it is time consuming to extract the patterns. And also, in sequential pattern mining, we look for the frequent pattern. So we may ignore many rare cases. Rare means not often, infrequent, okay. So all these patterns tell about some things that happen many times, but sometimes there are some patterns that don't appear really often, but that are really correlated. So if we use this approach, we will miss all of this. So maybe we don't do very good prediction. Okay, another approach that has been used is a DG, the Dependency Graph. This is another very simple approach I will explain here. We have the first sequence, A followed by B followed by C, followed by A, followed by C, followed by D, followed by D. And we have a second sequence, CC, ABC, BCA. So now we want to build a model to do some prediction. So what we do, we use a lookup window, or what we call lookup table, it's the same, of size 2. So that means we look 2 symbols by 2 to build the graph you can see on the PPT. Okay. So first we take the first 2 symbols, A and B. So what we will do, A followed by B appear one time here, appear also one time here, and also appear one time here. When we say size 2, that means A must be followed by B within the 2 next symbols. So here on top, A followed by B appear one time within 2 symbols. A followed by B appear here, and A followed by B also appear here. So that means, okay, so A followed by B within 2 symbols appear 3 times. So we have A with arrow to B with a 3. We don't count A followed by B here, A with this B, because it is more than 2 symbols after. It is 1, 2, and 3. So it does not count. Okay, so we say A followed by B appear 3 times. Now B followed by A as a 2 here because it appeared 2 times. So let's see. B followed by A within 2 symbols, and we have a B here, but there's no A. Another B not followed by A within 2 symbols, and here we have B followed by E 2 symbols after. So 1 and 2. So that means there's a 2 here. So in this way, we build a kind of graph that is called the dependency graph. So using this now, we can do some prediction. So for example, if we have A, we want to know what will happen next. So we can calculate the probability that B will follow A. So what that means, the probability that B follow A. So it will be B follow A appear 3 times. So because of this arrow here. Now divided by the number of times that we have A. So we have 4 times A in the training sequences. So 3 divided by 4. It is the probability that B will follow A. Now, if we look at the probability that C follow A, it will be the number of times that C follow A. So that means this number here. A appeared 3 times is followed by C, divided by the number of times that we have A. It is 4 times. So again, 3 divided by 4. So using this simple graph, we can do some calculation to predict the different symbols that may appear after A. And then, of course, we can choose the one that has the highest probability. So the advantage of this approach, it is quite simple. It does not use a lot of memory. We build a small graph with a few nodes and a few links between them. Another approach, very popular, is a prediction by partial matching, order 1. PPM, they can be order 1, order 2, and so on. So here we have again two sequences to train our model, and we'll build a graph that looks like this. So here it is like a tree, and at the first level of the tree, as you can see here, we have all the symbols like A, B, C. And we have on top of them the number of times that they appear. So A appear 4 times, B appear 4 times, and C appear 6 times. Then here we have a 2. It means A is followed by B 2 times. But here it is just after. There's no gap. Okay. So A followed by B, A followed by B appear 2 times. There must be one after the other. A followed by C appear 1 time. So A followed by C only 1 time. Then B followed by C, B followed by D, and so on. So this is how we build the model. Now again, we can use this to make some prediction. So now we want to calculate the probability that B will follow A. It is the number of times that B follow A. So it is here, 2. Okay, 2. So we have a 2 here. It's divided by how many times we have A. That means 4. So what we do here, we take the 2 and we divide by 4 that you can see here. So it gives you the probability that B follow A. Now the probability that C follow A, we calculate in the same way. So the number of times that C follow A, 1, divided by the number of times that A, 4. So 1 divided by 4. So here we can predict, for example, that B will follow A. That will be the prediction with PPM. And we say this is called the PPM order 1. Okay. Now we can also build a model PPM order 2. It is the same idea, but we will use 2 symbols to make the predictions instead of 1. So here we build a tree like before, but we use 2 symbols to make the prediction. So here at the first level of the tree, we have all the combinations of 2 symbols, one after the other. So AB, one after the other, appear 2 times. AC, one after the other, appear 1 time. BC, one after the other, appear 3 times. And then we have, like before, AB followed by C appear 2 times. So that's what it means. AC followed by B appear 1 time, and so on. So this is one way to build a model. We call it PPM order 2. So this model can be quite useful because unless PPM order 1, this model will use 2 events before, 2 symbols before to make the prediction. So it will use more information. But one problem with PPM order 2 is that sometimes maybe you don't have enough data, for example, to make the prediction. Let's say someone do BD, but in our model we never see BD before. So PPM order 2 maybe cannot make a prediction, okay, and so on. So that could be a problem. Also, maybe the predictions can be inaccurate if there's some noise. So let's say you do AB or you do BA. PPM order 2 will think these are different, but maybe in real life they are the same situation, maybe. It depends on your data. Is it important, the order, or not, for example? So if there are some noise, the order change a little bit, maybe the predictions are not good. Another model is the RK order Markov. It uses PPM from order 1 to K to do the prediction. So it is more accurate than the PPM order 1 or order 2, but the size will grow exponentially. So let me show you this. Here I have order 2. So that means I use PPM order 1, order 2 together to make the prediction. So on the left, I have PPM order 1. On the right, I have PPM order 2. So I take the 2 of them to make some prediction. So now, let's say I want to do some prediction. I want to know what will happen after AB. So I look under the tree for AB, and I divide the number of times I have AB followed by C, it is 2, divide by the number of times that I have AB 2, so it will give 2 divided by 2, the probability that C follow AB. Now I want to calculate the probability that C follow AB, B follow AC. So in the same way, I will divide the one of B following AC divided by 1 here, so it will give 100% chance here, and so on. So, and if I cannot do predictions with 2 symbols, then I will use ppm order 1 to do the prediction, for example. So for example, if I want to predict what happened after AD, there's no AD on the ppm order 2, then I will use for example D in ppm order 1 to do the prediction, and so on. So one problem with this is the size is exponential. If you use LK order Markov, what we call AKOM also, order 5 or 10, there will be so many possibilities. This tree will become very, very big. Another problem, also it is very strict. So the order is always must be followed exactly. Now, some limitation of the model I just discussed is that many of these models assume that each event depends only on the event before. So, for example, ppm order 1, for example, only do the prediction based on the one event before. But in some data, maybe you want to use 2 events before to do the prediction. Some models do that, but they have exponential size, like RK Markov, for example. And there are some improvements to reduce the size of this model, but few of them improve their accuracy. And many of these models are not noise tolerant, so the order need to be very strict to follow. It can be good or it can be bad. And some models are costly to update, such as the sequential patterns. To find the sequential patterns can take a lot of time. And also, all the models, they lose some information. So this is a key point. Okay. So when you build this model, like the sequential patterns, PPM or DG and so on, you always lose some data. You don't keep all the data from the training data. So that means when you want to do a prediction, you lose some data. You don't have all the original data. So maybe you cannot make a prediction. In other words, from PPM, for example, you build a PPM model, you cannot recover the original data because you lose something when you make the model. Okay. So, in this paper here, I want to present the CPT model here. It is a paper we published in 2013, and we also extended later in 2015. We present a model called CPT. The goal is we don't want to lose any data. Every time we do a prediction, we want to use all the data we have to be able to make a prediction. And we call this the compact prediction tree. It will be a tree to make some prediction, sequence prediction, and it will be compact because we don't want to use a lot of space. So our goal is to do accurate prediction. Our model will still be a little bit big, but it will be very accurate because we don't lose a lot of data. We don't ignore a lot of data. So our goal is to provide accurate prediction, more accurate, have a size that is not so big, and also to be noise tolerant. That means if there's some variations in the order of symbols in a sequence, we want to still be able to make a prediction. Okay, so our idea is we want to build a lossless model, a model where the loss of information can be controlled, so that we can use all the information we want when we want to make a prediction. We don't discard any information, or at least if we discard, we know what we will discard. So, and we hope this will increase the accuracy. So there are some challenge about this. We need to define a structure, an efficient structure, to put all the data from the training sequence. And we would like to have a structure that we can update incrementally. If there are some new sequences, we want to be able to update our model. And we want to have some algorithm that will do some accurate prediction, and if possible is also time efficient, is fast. Okay. So the model we present here is called CPT, as I said. It has a tree structure to put the training sequences, also some indexing mechanism to be able to search quickly when we want to do prediction. And to build the model, each sequence will be inserted in the model one by one. You will see with the next example. Okay. So I will show you some example how it works, how to build a model and then how to do prediction. It's really simple, you will see. So here we have 5 training sequences. Okay, A, B, C, A followed by B, A, B, D, C, B, C, and B, D, E. We want to build the model. So first, we'll take the first sequence. Okay, so at the beginning, we have an empty model. So we have 3 parts in our model. A tree that will have a root, and then we'll put the sequence there, the sequences. We have one lookup table, and we have one inverted index. And now we will build the model one sequence at a time. We'll add the sequence to the model. So here first we look at the sequence ABC. So what we do first, we add a branch in the tree with A followed by B followed by C. So in our tree. So we are training the model now. We put ABC in our prediction tree. Now we also have a lookup table. It is a pointer. Okay, so it says the sequence 1, if we want to recover from our model this sequence, the sequence 1 finish there at node C in the tree. So we have A followed by B followed by C, and here we have a pointer that say the sequence ABC finish here. It is the sequence 1. And we have one inverted index we will use to search in the tree. So it is a table, and we have the rows are the different symbols in our tree, like A, B, C. And the columns will be the sequence. And 1 means that a symbol appears in the sequence. So here we have ABC 1, 1, 1. It means that A, B, and C appear in sequence 1. If it was 0, 0, 0, it means they don't appear in sequence 1. Okay. Now let's continue. You will see how it works after. We do the second sequence to train is A followed by B. So again, we add AB in the tree, but AB is already there, so we don't need to create some new nodes in the tree. So they will overlap with ABC we had before. So we have A, B already here on the tree. So we don't need to make some new node. We'll save some space. And we put a pointer A to sequence 2 to say that if we want to read again sequence 2, we can go backward from B to A, and then we will find the sequence again from the tree, so we don't lose any information. So again, we need to update also the table, the inverted index. So here for sequence 2, we put 1, 1, and 0. That means that A appears in sequence 2, B, and C does not appear in sequence 2. Okay, so this is our table. Now we do the third sequences. A, B, D, C. So we need to add A, B, D, C to the tree here. AB is already there, so we don't need to create some new node. So we only add D and C here in the tree. And we add a pointer here to say that if we want to find sequence 3, we can read from the pointer here, go back C, D, B, A. We can read backward the sequence to recover the sequence from the tree. Okay, so then we update also the table. We say 1, 1, 1, 1 for A, B, C, D because all of them appear in sequence 3. Now we repeat this again for the next sequence, B, C. And then we will do the same thing again for B, D, E, the last one. So now we have finished building the model. That's all for training. Okay. So let me talk to you a little bit about this. So why we have the prediction tree? The prediction tree, it is to put all the sequences in the tree. The size of the prediction tree usually is not very big because there's a lot of overlap. Many sequences like ABC, ABDC, AB, all of them overlap. So AB is shared by all these sequences. So often this tree will be smaller than the original database. Here we have a lookup table. The lookup table is to quickly find the sequences in the tree if we want to find them. So we can read each sequence again backward by looking at the pointer, like sequence 1, it will be here, and so on. Okay. The lookup table is not very big. There is only one pointer for each sequence, so it is an array. It is not very big. And the inverted index, it is a table. There's a row for each symbol and a column for each sequence. So the size is not so big. And also, the table only contains 0 or 1. These are bits. So in our implementation of CPT, we use bit vectors, or bit set. We call bit vector or bit set. It is a data structure to make this table very, very small, so it does not spend so much memory. Okay, so this is about building the model. Now we'll talk to you about how to make some predictions. So we'll skip some details. Okay, so to do the prediction, let's look at some case together. We want to predict what will happen after AB. So the first step we should do is to look at the inverted index. We want to know in which sequences AB appear. So AB appear in sequence 1 because A and B have a 1 in the table. It appears in sequence 2 because A and B have a 1 under sequence 2. It appears also in sequence 3 because A and B have 1. But A and B don't appear in sequence 4 and 5 because some of them have 0 here. Okay, so after we find that AB appear in sequence 1, 2, 3, we find this here actually, okay, what I show. So actually, if we want to do this in a computer program quickly, as I told you, these are bit vectors, so we can do the logical AND. This is just some details about programming to find quickly what is the intersection of A and B. So we find S1, S2, and S3 contain A and B. Now we want to look at these sequences. So we use the lookup table, and from S1, S2, and S3, we read these sequences backward here, and we find what happened after A and B. So we find that after A and B, there is only C, C, and D. So C appear twice, and D appear once. So we count this in a structure we call the countable. How many times we have any symbols after A and B. So we find C appear 2 times after AB, D appear 1 time. So now we can make a prediction. The predictions will be that C will follow AB. So that will be the prediction of our model. So the idea is really simple of this model. The main idea is we don't want to lose any data. So we put all the training data in the prediction tree. And we have the table, the inverted index, to be able to quickly find the sequence that contains some symbols. And we have the lookup table to quickly find this sequence in the tree. And then we count what will appear after, for example, AB, to do the prediction, what will happen next. Okay, so here there's more details in my PPT about the complexity of making some prediction. Actually, it is very fast. I will go back to explain a little bit about this. So when we look in the table A and B, all the sequences that contain A and B, we do the logical AND of 2-bit vector A and B. It can be done, it has a linear complexity, okay? Then to look up in the lookup table for all these sequences is also done in linear time. And then to look up also is very quick to look in the tree and count the number of symbols. It can be very fast. Okay, now I want to show you some experiments from this paper. We use some database called BMS, FIFAR, COSARAC, SIGN, and Bible. Some of them are books. Some of them are sequence of click on web page. And they have different characteristics, as you can see on the table below. Different number of sequence, different number of items, different sequence length, and so on. We want to see on different kinds of data. Also, for this experiment, we compare CPT with DG, all k-order Markov, we call AKOM, and PPM order 1. We use tenfold cross-validation, okay? So each of these algorithms, we try to use the best parameter to get the best result to compare, to be fair. So we use two measures to compare the different sequence prediction model. The first one is accuracy. That means the number of times we do a good prediction divided by the number of sequences that we use for training. And the second one is the number of prediction we were able to do divided by the number of sequences. Why we use the coverage? Because sometimes, as I told you, some model cannot do a prediction. So how many times the model was able to do a prediction divided by the total number of sequences. Okay, so we use these two measures together to evaluate the models. Okay, so first we look at the accuracy. So we use the best parameter for each model, and we find that the CPT model we designed there has the best accuracy, sometimes much more than other models. So here, for example, on BMS, CPT has 38, DG has 36, is really close, and our AKOM has a 30% accuracy, and so on. On some database like SIGN, our model is really good at almost 35%, while some other model has a 3.5 and so on. So what does it mean is for such model, it is important to look at more than one or two symbols, and maybe the noise also is important. That's why maybe the model perform better. In terms of size, we also compare the model. Our model called CPT is quite big actually. Here we compare the size in terms of node, because some of them are graph or trees, okay? And we see our model is really big, but it's not the biggest. AKOM, K-order Markov, is bigger. But here there's a trade-off. Our model is quite big, but it has good accuracy. So we think that sometimes the accuracy is more important than the size. So that's why we were more interested by the accuracy in this work. Okay, we also evaluated the time for training and to do the testing. We call the prediction. So to build the model training, we compare the training time for all the database. And in some cases, our model is really fast for training. It's not always the fastest, but it is quite fast. Some other model, more simple, like PPM, are really fast. And in terms of testing, that means to do the prediction, the CPT model is not the fastest. Sometimes it can be 10 or 100 times slower than other model. But this is a trade-off actually for the accuracy. So if you want a model very fast, maybe you use a more simple model like DG and so on. If you care more about accuracy, maybe you can use CPT and so on. Of course, it depends on the data. I think it's important to try a different model. We also did some experiment about the scalability. If we have more training sequences, will it improve accuracy? The answer is yes. So here we have the number of sequences for each database, and we see the accuracy will increase. So in this PPT, I don't show what is the name of the database. I think it was BMS or COSARAC maybe. I'm not so sure. But you can see in the paper if you want. And we see here that as we increase the number of sequences, the accuracy of the model will increase from about 20% here to maybe 30. And our model will increase from about 30 to 35. So at some point, if you add more and more sequence, maybe the model accuracy don't increase so much because we have enough data. In terms of testing time, here we have the time. If we increase the number of sequence, it will take more time to do the prediction, and also for training a little bit, but not so much. So this model, we can think that they are scalable. Okay. We did another experiment using the CPT model. We want to see how many events we should use to do the prediction. So this is what we call the prefix size. That means how many events before to predict the next one. So here we have a chart on the FIFA dataset. If we look at two symbols to make a prediction, we have about 30% accuracy with CPT. If we use 7 symbols, we have 38 maybe percent accuracy. If we use 11 symbols, we have the accuracy decrease again. So by doing this experiment for one database, we can find more or less how many symbols we should look at to do some prediction. There are some other optimization in the paper. I will not explain all the details here. I just want to give an overview of CPT and CPT+. So if we want to predict what happened after ABCD, sometimes there will be some noise. If we want to look what is after ABCD, maybe we don't have the training data for ABCD. So we will try to remove some symbol. So from ABCD, we will try to remove A, remove B, or remove C, or remove D. So if we remove A, we have BCD. If we remove B, we have ACD. If we remove C, we have ABD. If we remove D, we have ABC, and so on. And also, we can remove two symbols. If we remove two, we have CD, BD, BC, AC, AC, AD, and so on, AB. If we remove three symbols, we have D, C, BA, and so on. So the idea here with this optimization we call recursive divider is that if we cannot make a prediction, we'll try to remove some symbols, and then we try again to do the prediction. So the idea is like we try to remove some noise. We think maybe some symbols are not important. We try to remove them and try to still make a prediction. So by doing this here we have some example of a chart. We have the accuracy and the number of symbols that we can remove. If we remove 2, the accuracy of CPT is about 30%. If we remove 3, it is about 35%, and so on. And also, the more we remove the symbol, what we call a max level, it will increase the coverage also. So the number of times we cannot make a prediction is about 30% if we use 2 symbols. We remove up to 2. If we remove up to 4 symbols, then we have 100% coverage. We can always make a prediction. So this is really helpful. Another optimization is to split the training sequence to make our model smaller. So if we have the very long sequence like A, B, C, D, E, F, G, we can use a parameter we call the split length, like 5, to keep only the 5 last symbols to build our model. So here we did some experiment for the accuracy. If we split at 5 or 10 or 15 and so on, the accuracy will not change a lot. But the testing time will if we split at 5, the time it will be much faster to do the prediction because the model will be smaller. The training time will be about the same, and the size of the model can decrease a lot. So if we split at 5, we have a model with about 40,000 nodes. But if we split at 40, the model is maybe 4 times bigger, and so on. So this is an optimization, sequence splitting, that we use to have a smaller model and we don't lose so much accuracy. This is the idea. Okay, so in conclusion, in this paper where we presented CPT, we designed a new model to do sequence prediction. And the idea, we want a model that is lossless, or if we lose some data, we want to control how much. And we want to use as much data as possible to do the accurate prediction. The model can be updated if there are some new sequences. It can be incrementally updated. And we have a few optimization, and we found that CPT is better, more accurate than some traditional model. But in terms of size, maybe it is not the best. In terms of speed, it's not always the best. But there's a trade-off, accuracy and speed and size, actually. Okay, so before I finish, I want to talk briefly about an extension of this model we call CPT+. CPT+ was proposed in 2015 in the PAKDD conferences as an extension of the work before. So here I will just briefly explain the main idea. Okay, so the idea in this paper about CPT+, we wanted to improve CPT. We want to make it smaller, CPT, make the model still smaller, and we want to increase a little bit the accuracy. So we have added some new optimization. Okay, so the first optimization is called compressing the frequent substring. So I will explain to you with an example. Okay, let's just have a look at the example. So what I do here, I have the same model I use for, I train my model like before to get the CPT model. And then I will look at the sequence that appear often in my database, the subsequence. So I can do the sequential pattern mining and find that AB appear many times in the database, A followed by B. So here I have highlighted A followed by B. So one idea to make the model smaller is to replace A followed by B by only one node. So I will show you. Let's have a look. Okay, so here I replace A followed by B by a new node that I call X to make the tree smaller. So let me show you again. So it was like this. And then I see that many times in the database A is followed by B. So I can replace A followed by B by a node I call X that contains AB. Okay, X is defined as AB. So what is the advantage of this? I reduce the number of nodes in the tree, the number of pointers between the nodes, and the tree will become smaller. I will save some memory. Okay, so this is the first optimization. It does not change the accuracy, it just changes the size. So here we have some complexity about this. I will skip the details. If you are interested, you can read or have a look at the paper for more details. Now, a second optimization to reduce the size of the tree is to compress what we call the simple branches. A simple branch, it is a branch in the tree where each node has only one child. Okay, so let me show you with an example. So here in the tree, there are some branches where each node has only one child. So B has a child C, and there's no other child. E has a child X, has a child A, and don't have any other child. So these are the simple branch. There are not many childs, only always one child. So what we do, we replace this branch by a single node. Okay, let's have a look again. So here I have B followed by C. I will replace by a single node BC. Let me show you again. Here I have E followed by X followed by A. I will replace by a single node with EXA. So this will make the tree much smaller because there are less nodes, there are less pointers between nodes. So again, this is only optimization for the size. Then this can be done very quickly. We only need to look at each branch one by one to compress the branch. It can be done really, really fast, very quickly. Now, another optimization, it is what we call the improved noise reduction. So in CPT, there was one optimization where we remove some symbol to do prediction. So here we improve this. Instead of removing all the symbols one by one, we only remove the symbols that are the less frequent. So if we have A, B, C, D, the sequence, and D is not really frequent, don't appear really often. So we'll try to remove the symbols first that are the less frequent, don't appear so often. And we find that this usually gives better prediction, because if a symbol don't appear so often, we can think that maybe it is some noise, so we don't need to keep it. Okay, so again, we did some experiment to compare CPT plus with some other model, DG, TDAG, I did not explain, LZ78, PPM, RK order Markov. Okay, so I did not explain all of them, but these are all some traditional algorithms that are quite popular. So we use different databases, you can see in the table there. So we compare the accuracy. Here we find that CPT is often has a better accuracy than CPT. Not so much, but in some case by 3 or 4% maybe, or 1 or 2%, it depends. And sometimes some other models are better, like here, RK order Markov is better for the Bible database. So It always depends on the nature of the data. In the Bible database for the words, we can think that the order of words is really important. In our model like CPT, CPT+, the order is not so important. A followed by B, B followed by A is considered as the same actually. Okay, so depending on the data, some other model may work better. In terms of scalability, we did again some experiment. We increased the number of sequence and we have a look at the size of the models. So we find all the models, the size increase more or less linearly with the database. So in conclusion, sequence prediction is a fundamental problem. When we analyze the data, we will have a sequence and we want to do prediction. What will happen next? It can be applied to predict where some people will drive the car next, which tourist spot a tourist will visit in a city, where you will go, what you will do, some activity, and so on. Or it can be used to predict the words in the text and many other things. Okay. So these are the models I wanted to present today. If you want to try them, they are offered open source in Java in the SPMF software. It is an open source library. You can download, use. You can also, it has a graphical interface, it has a command line interface, so it is easy to link also with other programming language. You can find the source code, the database, to test the algorithm on the website, so if you want to extend to do some research. All the code of all the algorithms I discuss is in this software, so you can extend and do other research project with this. So this is the software. It's really simple to use. It has the interface, user interface, many algorithms. Okay, so that was the end of my presentation. I hope you enjoyed this video. I will post more video later. Thank you for listening.